some cool stuff on Twitter. You can find Dale there as well. Twitter, if you haven't jumped onto it as an educator, is such an amazing education sharing hub. And Dale's pretty active on there too. So if you wanted to check out some cool physics stuff and all that kind of thing, you can see that. So thank you, Dale, for joining us tonight. And with that, I'll hand it over to you.
All right, perfect. Thank you for the very, is my video off?
Your camera is off.
Sorry, there I am. Thank you very much for attending. I know it's the Thursday night before the break. I'm sure you have plenty of things to do in order to finish up tomorrow and prep for your time off. My name is Dale Simnett. I'm a teacher at Castlebrook Secondary School, Eastside Brampton, Peel District. And I'm here to talk to you a little bit about what I've been doing in problem-based learning. So what I wanted to share with you tonight are a couple things. One is a series of tasks, and second, sort of 3 different ways I've used problem-based learning in the classroom. So let's jump right into it. This is a drone. A drone is a pretty simple little thing. It's got 4 electric motors. You can see that little battery strapped to the top, a remote control down at the bottom. This is Amazon's delivery drone. This is what they propose will be delivering all your packages in the future. This is pretty interesting. This is a Chinese military drone. It fits in the back of the truck, and then all of a sudden they just fire out, and all of a sudden you have drones that can go disable air defenses and bomb targets. They actually used these in the recent Azerbaijan war. So this is the potential unmanned aerial vehicle that could be flying around Toronto in the next 10 to 20 years, carrying passengers from rooftop to rooftop. So the super rich do not have to bother with the people down at street level. And this is actually quite interesting. A Chinese village just a couple weeks ago paid $12,000 for this drone, and they attached a gas tank to it, and all of a sudden it was a aerial flamethrower they used to kill wasps in nests high up in a tree. So my point behind this is that there might be jobs with drones in the future. And that's sort of one of the things I like to concentrate on in problem-based learning, something that might get students a job. So the first problem we are going to break down tonight is, how does a drone work? So what I would put to you right now is, what questions would our students need to ask, or would you need to ask, in order to figure out how does one of these drones work? So feel free to turn on your speaker or post on the chat. What questions do you think students would need to answer in order to figure this out? What is its power source? All right, where are we going to get energy? What is its purpose, payload? How does it fly? So how does it generate lift? What provides the force? How do you control it? The shape of the blades? How does it steer? That's actually really interesting and quite complicated. What's the range? How does it see? How accurate it is? What forces cause it to lift? How does it balance? All right, what tech does it use? You've come up with some pretty fantastic questions, and these are the type of questions that that we would like our students to ask, and we would like our students to answer in problem-based learning. So when I first went into the drone world, these are the questions I sort of asked. Now, the first question was, how should we deliver a package? Now, this was really my own selfish need to involve kinematics in it. So we talked about a truck versus a drone and how the shortest distance between two spots is displacement. So we talked about how a truck might travel a further distance than a drone, how drones track closer to displacement. The second question, how do you create lift? So I guess I should intro this in saying that I designed this task for a 4C physics course. So in how do you create lift, we sort of get into the Bernoulli's principle, air pressure, those type of things. How much lift force is created? So back to the old Newton's laws. How does a motor work? And then how do we generate electrical energy for the motor? So I actually started out with how should we deliver a package in this little assignment I had about comparing distance and displacement for a delivery. And then I started talking about drones, and then I kept talking about drones and ended up sort of going through this circle. So what I wanted to go into just a little bit is how I went about designing the tasks that you would use to address these 5 questions. So first question, how should we deliver a package? So the first step, and I feel the most important step to problem-based learning, is adding context to the curriculum. So the first step is just making it real for our students. So you'll see here, I have a little bit of an introduction about the original assignment I had, a shipping facility in Amazon. They want to test out their drone flight. I added a section on job prospects because I'm big in, yet again, relating these back to the real world. So how much do you get paid for using a drone? And resource acquisition. So I'm big on just students finding their own source of text or video that they can use to help solve the problem. Now, just to get formalities out of the way, if you have any questions at any time, feel free to post them in the chat. I also don't mind if you just want to interrupt and turn on your mic. So whatever you feel like doing. So for each of these questions, just to start, I would add a bit of context. The next thing I would do, so for the second assignment, and I would do these for each of the tasks, but the next thing I do is layer on learning goals. So how does it relate to the curriculum? So the next task number 2 was how do you create lift? And we have the relationship to, of course, Newton's third law, pressure, Bernoulli's principle, essentially what theory they'll need to know in order to address the problem. The third thing I do is I add our application of theory. So generally with these tasks, I like to try to keep what the students need to do fairly, like, not task overload, but I want to give them a few application questions just so it really gets to how the theory applies to the problem. From there, I try to add a pictorial representation, so some sort of picture that has to do with the problem that they need to label. I'm big on label diagrams and especially labeling diagrams with theory. So it works out well if you come up with some diagram associated with the problem and ask them to layer on how it relates to the problem in the theory that you ask them to talk about as well. And then last step is the mathematical representations. So in this case, this is how to generate electrical energy for our motors. So this is where I would get into the sort of mathematical problems, and I just outline whether I want them to do a second law equation, if I want them to calculate really whatever relates to the problem. So when creating these things, I add an introduction, learning goals, picture, application, and math. And all of a sudden, oh, sorry. Now, the great thing about mathematical representations in these problem-based learning tasks is there is such fantastic math out there. I thought that figuring out how to get them to calculate stuff relating to drones might be the most difficult part of the task, but it was actually really easy. So this is the DJI E7000 drone motor. And if you look, well, I have a little engineering secret. A lot of engineers just go to catalogs and look at some values and pick things for their design. And that leads to a lot of catalogs with a lot of really good information. So if you look here, they have maximum thrust for a drone. They have the recommended battery, which relates to the voltage of the drone, maximum allowable current. So if you look, there's really good mathematical information about all these real life mathematical problems that lead to some really fun and interesting calculations. This actually doesn't relate to the drone motor I was talking about, but when I found this chart, I was in love. I mean, this was fantastic. It talks about your throttle position. It relates it to current, power, thrust, efficiency. Like, these are fantastic things that we can use in our mathematical representations. Oh, sorry, this slide's a little bit messed up, but this is the battery that would actually be used for that drone engine. And yet again, if you look at the information they give on the right, it's actually really applicable to grade 12 college physics. I'm sure some of you might have seen the formula in the top right, current equals charge over time. Now, sometimes in the past, I've gone through this and I actually really like the formula. I think it's pretty interesting, but my students have not necessarily always thought so. But if you look at what this battery provides, it actually tells you how much charge is in the battery. And if we go back to that motor, which tells us our maximum continuous current, we can actually calculate how much time this drone will run for using one of sort of the fundamental electrical physics formulas. So I think one of the greatest things, and I'll let you try one of these problems in a minute, is how applicable physics is to real life. I know it shouldn't be a shock, but I found it really easy that as I went through this process, physics is everywhere. Surprise, surprise. Now, so what you see on the right there is essentially what one of my problem-based learning tasks will look like. The introduction, the learning goals they will need to know in order to address the problem, the mathematical representation, so what I want them to calculate. This is sort of a cheat just because I wanted them, maybe it should have been under pictorial because it's a right-hand rule, but math it is. Application of theory and your pictorial representation. So how do I use this in my actual class? Essentially, what I do is I introduce the activity, I provide context, and this context can be different, but what I actually have the students do for the drone task is I have them create a business. I ask them how much, so one business they've created in the past is a drone which will deliver a brand new pair of sneakers to your door. We calculate how much load is required. How much load is required? Sorry about that. And then using that, we can estimate the weight of the drone. We can estimate the amount of force they need in order, like how much lift force is required. And it just provides that introduction. Then I go and I teach the content like I normally would. So we'll talk about current, voltage, magnets, motor principle, whatever demonstrations I would normally do, whatever activities I would normally do, whatever small group work I would normally do. So I generally use a PBL for context, teach however I normally would, and then at the end, it provides a consolidation of their understanding by solving the problem. We bring it back to drones. Now, the other thing is labs now become a part of the problem. So the lab on the left, the drone thrust, the lab I do here is essentially a Newton's second law lab. And I was fortunate enough to have a fan cart in my department. I'm not sure how many of those you might have, but a fan cart is essentially a horizontal drone engine. So I would take a normal Newton's second law lab, use the fan cart, and all of a sudden we can calculate how much thrust the fan can create using Newton's second law. So a lab that I would typically do in a normal forces unit all of a sudden becomes a drone lab that I can apply to whatever problem-based learning I might choose to do. So the question in the chat, is this all within one 75-minute lesson or over several lessons? So the drone tasks that I just showed you, and I guess I should have mentioned this earlier, this would have been my full unit. So in this case, the units have become, instead of the problem following the curriculum, I have the curriculum following the problem. So essentially our problem is how a drone works, and that's what I start off with in the first or second week of school. And then as I go through those questions I talked about earlier, I teach the material that relates to that question. So we don't have a forces unit or a motion unit or an energy unit. We essentially address a sort of motion related problem, then we address a kind of forces related problem, and then we talk about energy and forces combined. But I'm not actually following my traditional units, I'm following drones is my unit. Thanks for that question. Any other questions so far before I try to motor on? So typically my drone unit will probably take a month and a half, maybe. To be honest, my grade 12 college course, I do a unit on drones and a unit on building a house, and that's it. And that covers probably 90% of my regular curriculum, 90 to 95%. Now, I'll talk about this a little bit later in that this process can become very inquiry-based. If I wanted to say, all right, what problem do we want to address? And then start just like I started this presentation, all right, this is the problem. What questions do we need to ask to solve that? I have not tried anything inquiry-based yet. But it's very possible that you could use this process and develop something along those lines. Now, so that was basically talking about using a problem as your unit. So drone-based unit, building a house as a unit. Now, the second type of problem-based learning that I've tried is using a PBL as a course theme. So this was one I used in grade 12 university physics. And it was pretty interesting. The question was, how do we get to another planet? And amazingly enough, this relates to more or less all the units in your course. Arguably, quantum might be a little bit harder to apply, but I'm sure if you really look for it, you could probably find it there. And if you don't know how to get to another planet, the biggest thing is in the top right, the Hohmann's transfer orbit. If you want to take a path to another planet, that's the path you got to take. It's most energy efficient. But so the way this worked is I would go through sort of my regular units, but at the beginning, I would introduce the problem, the very beginning of the course. And then as we go through, we sort of address our individual tasks related to how to get to another planet. So in our kinematics unit, we talk about where is zero. I'm sure everyone here has probably talked about how you should always label a reference point in problems. Well, in space, that's really, really important. And it's a really, really interesting question. Where do you put zero? Because there's a whole bunch of zeros you can use. Where are we and where are we going? In a forces unit, we can talk about orbital velocity, gravitational force, how gravity changes as you move from one planet to another. So what we are going to do is we're going to take a look at something related to the point I made earlier. We're going to do some kind of simple, but kind of really interesting math that came out of this task, how do we get to another planet? So in a minute, Chris is going to send us to breakout rooms. We're going to have 10 minutes. Now I'm going to post, Chris, how many groups do we have?
I'll make 7 groups of 4.
7 groups of 4, perfect. So just 1 second. So I've just posted several Jamboards. So group 1 and 5, you'll be using the first Jamboard. The first group using that Jamboard will use slides 1 and 2. The second group using that Jamboard will use slides 3 and 4. So you have 2 slides in order to do your calculations. Now, there's going to be 3 roles I'd like you to assign. One is the recorder. So they are going to manage the Jamboard. I would suggest whoever has the nicest screen penmanship, you assign them to be the recorder. That probably wouldn't be me, but hopefully one of you has beautiful screenwriting. I would like you to assign a manager who's responsible for getting everyone's input, and a speaker who essentially before the end of the 10 minutes, just gather any thoughts and then bring them back to the group after the 10 minutes is done. Now we're going to have about a 2-minute warning with 2 minutes left. And at that point, it doesn't really matter if you're done the task, but on the 7th sheet of the Jamboard, there is an exemplar. So for the last 2 minutes, wherever you are, you can look at the answer and compare your work to what I've come up with. Please don't judge my work too harshly. I would appreciate it, but I'm sure I'm missing something or another. Now, these are the learning goals related to the problem. So you're going to have to bring your knowledge of projectile motion, Newton's laws, universal gravitation, and forces in free body diagrams. So let's hope that doesn't sound too daunting for some physics teachers. And the task. So the information that you see at the bottom is actually from NASA's Jet Propulsion Laboratory. So anyone can access their online database, and they will provide the coordinates in space and the velocities. I selected Cartesian coordinates, so in the X, Y, and Z, sorry. We are going to ignore the Z axis as I normally do in class, but using the position in the X, position in the Y, velocity in the X, velocity in the Y, I would like you to determine the position and velocity of the Earth at a unknown time in the future using only JPL's data. So figure out, you will all be assigned one task. You are either figuring out D2X, D2Y, V2X, or V2Y as a function of D1X, D1Y, V1X, V1Y. Hopefully that's clear enough. So, Chris, you want to push everyone out and let's get started.
Sure, and just a double check, if you're not sure which link to follow, you can just type a note in the chat. And when I hit the open all rooms button for the breakouts, you will be Shazammed into your breakout room. So any last question before we go? Okay, here we go.
I wasn't exactly sure how that would go. I hope you enjoyed it a little bit. I hope you had a chance to check out the exemplar on page 7 of the Jamboard. Now, what's nice about this is it's a really fun little mathematical problem that will kind of blow your students' minds, but as they move forward with it, hopefully they can see a really nice real life application of kinematics. Now, what do we do with this equation you just developed? So this is an Excel document I created, and up at the top, you'll see the JPL data. So it's a really good opportunity to teach students a little bit about entering formulas in Excel if everyone's Excel proficient. And you'll see
Dale, are you able to share that with us?
Oh, am I not sharing? Oh, sorry. My fault. All right, can we see that?
Mm-hmm. Yes.
Yes, we can.
Okay, so in the cells on the right where it says dx new, dy new, vx new, vy new, in there I taught my students how to use formulas using Excel, and we would take the initial position and velocity data and we'd get it to spit out the new position and velocity, in this case after about 10,000 seconds. Now, using that, we calculate the position and the velocity every 10,000 seconds, and then we plot it. And the next thing you know, we have a beautiful image of the orbital path of Earth. Now, if we take the planet where we begin, the Earth, and we also put that equation in for the planet that we're trying to get to, Saturn, we get two beautiful, well, I guess ellipses ideally, but circles in this case. And we can actually start graphing or using Excel to calculate some of the things we need in order to figure out the physics of getting from one planet to another. So I think the point is, if you go looking for it, there's some really neat math you can do out there and some really nice applications of physics that are at our students' level with a little bit of guidance. Now, when I did this in class, typically it took about 2 periods for them to sit in groups and work it out and figure out all the little intricacies in order to develop this equation and then put it into Excel and then create the orbital path of our planet. Now, So just moving on, why you should try PBL. First, I taught 4C physics students, and I was telling them about all these things, and I'd see it in their faces. What does this have to do with anything? And I think just adding that real life context right at the beginning, all of a sudden they can see the applications in real life. Why else would we want to do it? The curriculum says so. So they moved the STSE expectation right to the front of the curriculum. It's number 1. And that's really what this addresses, getting all this knowledge and all these skills we're trying to impart to them, getting them to actually think about that when they're looking at all the theory, when they're doing all these mathematical questions we ask them to do. I like to focus on tasks people get paid for. I think, especially in the academic streams, we can get a little bit far away from that. And I think there's lots of opportunity to look at real careers like drone technician or building a house or an engineer that might work for NASA. I think there's more skills we can impart if we actually do something that's real life related. And at the end of the day, all your students will be jumping up and down, not wanting to leave your classroom, and giving you high fives, because it's a lot of fun for students. And I think personally, there's nothing more interesting than a challenging problem. And real life has tons of challenging problems that can make everything a little bit more fun. Now, the third task, we're not actually going to get to it because that last task took a little bit longer than I sort of thought. But the third approach I've used, problem-based learning, is on a unit or a lesson-based basis. So you take one unit of your course, energy, find a problem that relates to energy and introduce it right at the start of the energy unit, and use that as the context as you develop the energy transformation equations, the mathematical equations. And thanks to the Perimeter Institute, a fantastic session they had the other day on, they developed a black hole escape room. Escape room challenges is something that I'm going to try out in the near future in my courses. So an idea, and check out Perimeter Institute's stuff, because it really is excellent. All right, so we're going to skip the second group problem because I don't want to take you too far after 8 o'clock, and I'm not exactly sure. Oh, it's 8:01 now. So now, just two things that I'm thinking about in terms of extending the PBL process, making it all inquiry-based, picking a problem like how do you get to another planet, and having the students sort of ask the questions as you go throughout the course. I think it's really interesting. I've just developed an assignment called SWASH, and that stands for Simnett Wants a Side Hustle. So how can we actually teach them the skills that they would need to wire a house or start a drone company, or so that right after high school, they could jump into something that will make them some money. Now, I'm looking forward to trying it with my 4Cs. I'm hoping they come up with some good business opportunities that I can start in the summer. And so we'll see where that goes. There are cross-curricular activities, opportunities everywhere. I've thought with that, how to get to another planet, it would be interesting to bring in a 4U functions course and actually plot some of these functions like the force of gravity as you go from one planet to another. There's plenty of business cross-curricular activities. And another idea I really like that I've started to implement in a couple of courses is the expert contact. So why not contact someone at the Jet Propulsion Laboratories and say, this is what we're doing in our class. How does it work in your job? What do you do? I actually contacted a quantum physicist called Thomas Juffman a little while ago. He threw like 150 atom molecules at a double slit, and saw a basically saw a real life version of the double slit experiment. And he was happy to talk to my class and describe what a quantum physicist actually does. So just bring, yet again, those contacts outside of the classroom into the classroom. Now, I'm going to be sharing a folder of resources. So what I've included in there is the learning goals I've used for the 3U, 4U, and 4C course. So if you want to just copy and paste them into a new problem, they're there for you. The PBL template, which basically is the headers that I talked about earlier, the learning goals header, the basically the structure for those activities I showed you earlier. The 2D diagnostic task that we didn't get an opportunity to try, what I've done in 4U and 4C. So feel free, maybe if you're only teaching one course, try something out, see what you think. If you ever need any help, please let me know. Now, things I've thought about going and thought about doing soon is a 4U unit on how to build a quantum computer. I think it would be a really interesting problem to analyze, and I bet it relates to every single unit in 4U physics. I just don't know how yet. And I'd like to thank the people at Castlebrook, especially my physics colleagues, Alexis Howell and Evan Norris, for helping me develop all these things. Obviously, we use a team approach. Chris Meyer for giving me and the Ontario Association of Physics Teachers for giving me the opportunity tonight. And thank you all for showing up the day before the winter break. So, and trying my kinematics related problem on a Thursday night. So if you have any questions, I'm happy to stick around. If you gotta go, feel free to go. And I'm happy to hear any questions or comments now as well.
Thanks, everyone. Dale, thank you so much for challenging us and introducing kind of context to, because I think you're right, you get away from why, and the kids are always asking like, why do I have to learn this? And so it's nice to be able to give them some context to that. So thank you so much for sharing tonight. If anybody wants to stick around, we're gonna do like just similar to last time. So if people want to stick around and chat for a few minutes, we'll be here. Otherwise, have a wonderful night and happy holidays to everybody. And thanks so much from the Physics Hour Committee from the OAPT. And thank you, Dale, again.
Thank you, Dale.
And here, let me just post the link to the shared resources for everyone. And there you go. You can check it out. I'll update everything there as well. So thank you, everyone, for attending. Thanks, Ashley, for the kind words.
And just a quick thanks to Ashley and Rochelle and Melitza, and Adam isn't here. They are the team that helps to organize our Physics Hour sessions. So they've been doing a fantastic job this fall in the place of our conference. So a big thank you to that group.